Okay, so we're going to take those areas that we've calculated, or sorry, let me rephrase that, because otherwise I'd be redundant. We're going to take those regions that you found the area of and start spinning those puppies around lines and creating three-dimensional volumes. This will be fun. The reason it's so complicated is because we can spin it over the x-axis, we can spin it over the y-axis, we can spin it over any other horizontal line, we can spin it over any vertical line, we can do it in terms of x, or we can do it in terms of y. So there's a whole bunch of combinations there. And we'll take, I'm going to go fairly slow through this and make sure that you're with me. And hopefully I have examples of just about every one of those possibilities. Okay, so as I said, we're going to use, these are called solids of revolution or volumes of revolution. We're going to use two different methods. One is called the disk method. The other one is called the washer method. Part of the challenge is going to be recognizing which one you should be using. I have some methods to help you recognize that. And then for today, you should try to do something nice for a stranger. Not somebody you know, just a stranger. Give them $1. Compliment them, or put gas in their car. Share your lunch with them.
That sounds like money.
Now you understand why this world is in severe decline. Okay, so we'll start with the disk method. That is a disk. If you had a good geometry teacher, you would also know that as what other shape? Say again? A cylinder, correct. How do you find the volume of that cylinder? Well, let's back up. What information do you need to know to find the volume of that cylinder?
Radius and the height.
Beautiful, radius and the height. So if you had the radius and the height, how would you find the volume of that yellow cylinder? Also, we're going to call it a disk. Yes?
Pi r squared times h.
Beautiful. Couldn't have done it better myself. Find the area of the circle and multiply by how many circles you have stacked on top of each other. Beautiful. You know all this, right? Yeah. I know you had a good geometry teacher.
Yeah.
Yeah, okay. How about that bad boy? Technically speaking, that is called an annulus. We're going to call it a washer just because I'm uncomfortable with the word annulus for some reason. I don't know, it just doesn't sound right. How would you find the volume of that washer?
You subtract the inside cylinder from the outside one.
Hot diggity. Say that loud and proud so the video and everybody else can hear you.
You subtract the inside cylinder from the outside one.
Good. So that hole in the middle is actually another cylinder. So if you subtract the big cylinder from the little cylinder, you have the volume of the annulus, also known as a washer. Any problems? Excellent. Now this is calculus. So what do you, yes?
Could you factor out stuff and just make it pi h times r minus r squared?
So this guy doing math already. We're not even ready for that, but you hit the ground running. Could you explain that to the Luddites in the group, please?
So you take out the pi h.
All right, hold on. For the visual learners in the crowd, based on what Andrew told us, this would be capital R squared times pi times h minus little r squared times pi times h. And your question is?
You can take out the pi and the h. Is that as far as you can go to reduce it or simplify?
Well, I would say at this stage, yes. Sorry, I'm going to answer your question in a roundabout way. You could simplify that more. Do you need to? No, because it would make no sense. Okay. That's the difference of perfect squares. You could factor it into big R minus little r times big R plus little r, but that's not going to help us. This will help us. We'll come back to that later. This one, by the way, pi r squared times h. We're good to go. Okay, so seeing that this is calculus, what are we going to change in calculus from what you did in geometry? No. Easier than that. Is that going to say that?
Throw it on axes?
That'll come naturally, yes.
Integrated.
Yes. Good. Because you wouldn't do that in geometry. My freshman's head would explode if I tried to have them integrate. Is that big, fat, thick disc going to work for us?
I don't see why not.
I don't see why not. Okay, well, we'll see. Well, I've got some pictures that'll show you why it doesn't work. What are we going to do with the thickness of that disc? Say again? Great. 7 people answer. I ask for clarification because you're all talking at the same time, and then all of a sudden everybody's struck.
Make it infinitely small.
Good. We're going to shrink that height down to almost 0, which means we're going to refer to the height as either dx or dy. But we'll get to that in a couple minutes. I just want to make sure your geometry skills were where they needed to be. Excellent. Okay, so here's what's going to happen. Remember that representative rectangle we started talking about, and none of you, or not none of you, very few of you have decided to use it. Well, now it becomes important because if I take that rectangle and I've over-exaggerated the size of our representative rectangles because we talked about already the fact that we want it to be very skinny. But if I take that representative rectangle and I spin it around the axis of revolution, we get a disk. And you might see where we're going with this. If I take the axis of revolution and I spin it around if I take the rectangle and I spin it around the axis of revolution, I get a disk. If I take all those representative rectangles, and what would I do with those, Chris?
What was the question?
Just give me the same answer you gave before.
I'll integrate it.
Yeah, you would integrate it because that's an accumulator. We'd add all those bad boys up and we'd be good to go. So we did that already. Volume of a disk, pi r squared. We're going to start easy. And the easiest case is when we're talking about disks. Pi r squared times w would be width. It could be h. It depends on whether the rectangle's going up and down or left and right, vertical or horizontal. We'll go with w for width. And this is what we're going to do then. Notice that little yellow representative rectangle in the center of that. When I spin that representative rectangle, I get a disk. It's yellow. All the other ones are blue. And when I'm done, I have that little planter-looking thing on its side. Do you think that's good enough for this class? No. Why not, Yair?
Because it's not like smooth. I don't
Good.
know.
We would like it to be smooth. So it gives us an exact value for that volume. This is very similar to what we did with Riemann sums. If the representative rectangles are too fat, then we get all those corners. We don't want them to be fat. We want them to be very, very, very skinny, like we talked about already. And we're going to shrink them down to 0, which is where the integration process comes into play. Okay? So you'll recall when we did area, my goal was to find the area of one rectangle, and then we integrated to add up all the rectangles. We're going to do the same thing with volume, except instead of finding the area of one rectangle, we're going to find the volume of one disk, and then integrate to add up all the disks. Are you okay with the concept so far? Okay, good. We want it to look like that. Notice the difference from the right one, where it's got all the sharp corners and it's not a very accurate answer, whereas we would like it to be the blue one in the middle where it's smooth. And we'll get that again by taking delta x and making it as small as possible, or increasing the number of disks up to infinity, one or the other. Width goes to 0, or number of disks go to infinity. Are we okay with the concept so far? Yes or no? We're good? Seems pretty logical? All right, so then what we're going to do is we're going to dive into this bad boy. Yeah, we talked about, just talked about that. Okay, come on, let's move on. Ooh, I got some cool pictures to show you. Watch this. Hopefully I can get it to work. Nope. Come on, Reedy. How do we do this? Go here.
Delta x is the width of the.
Say again, Andrew, I'm sorry.
Is delta x the width of
The representative rectangles?
Open it on.
You can open it? Yeah, but you don't have the program to run it. That's the problem. Why can't I click on it? Because it's giving me the... Oh, there we go. Okay. Yeah. Yep. No. Donate. Okay. All right, maybe we're not going to do this then. Because we're experiencing technical difficulties. It worked like a champ on my old board. Okay. Oh, there it is. Okay. You'll have to forgive me, this program is very old, but it still does a nice job of demonstrating what's going on. So the way I set this up originally with it being horizontal, it doesn't matter. You'll see whether it's horizontal or vertical, you get the same result. So here's our representative rectangle. And then when we spin that puppy, we make that little washer thing. Okay. Now, what we used to have to do is we'd also teach the shell method, which was a train wreck. We don't have to teach the shell method anymore because it's not in the syllabus for AP Calc. So we're going to get that. All right, while we're on this slide here, let's reset that. Let's go to display, erase all traces. What happens if I move the representative rectangle off the axis of revolution? In other words, I drag this puppy over here. And then get rid of those traces. What happens when I spin that thing?
It's a washer.
Yeah, you get a washer, correct, which we'll get to then. Okay, we'll save that for later. Okay, so let's get out of here then. And I'll come over here. All right, so show you what this looks like. We're just going to dive right into it. So before I click and show you what this is, part of the challenge you're going to face is getting a good picture. So sketch that. I would like to tell you that the difficulty in these problems is drawing a good sketch and setting up the equation, and the derivative and the integrals are easy, but I would be lying to you. The integrals aren't always that easy. While you're sketching that area, I need you to do two things. Number one, could you shade in the area we're going to spin? And number two, could you draw a representative rectangle in that region? Remember, you're just doing a sketch. It doesn't have to be 100% accurate. So there's two different things going on. One is establishing the region, and number two is what it looks like when you spin it. So the region is just going to be the stuff above the x-axis. If you're feeling saucy, try drawing the three-dimensional figure. I dare you. Also, to make our lives, never mind. I was going to say find the points of intersection, but we really don't need the points of intersection. Good, right? Good color choice there. Representative rectangle? I'm doing good. Wow. Very nice. Yeah. Good. Excellent. Change up the colors. All right, we're good. So, should look something like this. Now, I wish I could claim that I drew those. I did not. I cheated. But the yellow region is our region that we're going to spin around the x-axis. And then the green thing is what it looks like after it's been revolved. Okay. Number one. Oh, you know what I would also do? When I'm doing the problems, I like to throw one of these in there. I like to do one of those. Whoops. What am I doing? Come on, Rita, you're better than that. Okay, pens, red. Good. I like to do one of those. Okay, so I know what I'm spinning around. Questions I ask myself when I start these problems. The most important question is, I want to make sure that my rectangle is perpendicular to the axis of revolution. If it's not, I screwed up somewhere. That's number one. Number two, second question I ask myself is my rectangle touching the axis of revolution? Is it? Yes. If the answer to both of those questions is yes, then I know that I'm going to use the disk method, hence the title of the slide. If it's not touching the axis of revolution, then we're going to do a washer. That comes later. Okay, so what's the radius of that blue disk? Which is? Beautiful. So our goal is to find the area of that, sorry, not the area, the volume of the disk. In order to find the volume of the disk, I need to know the height of the rectangle, because the height of the rectangle is the same as the radius of the disk. I don't care about the height of the disk anymore, because we're always going to make that height either dx or dy, because we're going to make it really skinny. Okay. Good with the concept so far? You're talking about the height of the rectangle, not the height of the disk, right? So if I'm understanding your question correctly, you're bothered by the fact that that height is different than this height.
Yes.
Right. It's taken into account because the height is actually the formula. Okay. So you can think of the height, instead of a numerical height, you're thinking about the height as being f of x. It's the function. Okay. So the area of that rectangle is x squared plus 3 dx. However, we don't necessarily care about the area of the rectangle. We want the volume of the disk. So notice that the height of the rectangle is the radius of the disk. Many of you will forget the two crucial things. You'll forget the squared part, or you'll forget the pi part. Pi r squared times the height. The height is easy. The height's always going to be dx or dy. Forget about it. So this little expression here is the volume of one disk. Then I kick in with the integrator, or sorry, the accumulator, which is an integral. And I get that monster. Okay, so let me talk about each of those components. Number one, I'm taking rectangles from -2 to 2. I don't think that would be a big surprise to anybody. Since pi is a constant, I moved it out in front of the integral sign, and don't worry about it. I'm not going to include it in my calculations because it makes things ugly. However, you have to remember, if you fn int, or even if you do it by hand, you have to remember to multiply by pi at the end. Okay, don't forget that pi is sitting out in front. Just as a quick review, I obviously fn inted this answer, but if you were doing this by hand, what's that squared? In other words, when I multiply it out, what do I get? Quick review here.
X to the 4 plus 3x to the 4. I mean, x to the x squared. 6x squared plus 9.
Well done. Okay. Again, if I was doing that integral by hand, if for instance you had a non-calculator quiz, you'd have to do that by hand, multiply that out, because you can't do that as a UDU. Then go crazy. Well, that would be fun. Plug in 2 into that, plug in -2, subtract, get an answer. Or you could just have fn int it and get 253.841. I'm not necessarily concerned if you can find the answer, because I know you can find the answer. I'm more concerned about, are you going to be able to recreate that method for finding that volume? Yes or no? We're good. Okay. So again, that's the easiest one. That is where your rectangle is vertical. I forgot to mention that. If your rectangle is vertical, everything is in terms of x. We've talked about that already, so that's number 1. Number 2, is your rectangle perpendicular to the axis of revolution? Yes, then we're good to go. Number 3, is the rectangle touching the axis of revolution? If the answer is yes, then we're doing a disk method, which makes everybody happy. Okay, any questions before I move on? Beautiful. Washer method. So we go through that same process. Is my rectangle vertical or horizontal? It's vertical, so I'm working in terms of x. Is it perpendicular to the axis of revolution? Yes, I'm good to go. Then, is it touching the axis of revolution? If the answer is no, then we get a washer like I showed you in that little program before. And based on, I think, Andrew, you did this, right? The volume of that annulus or washer?
Yeah.
Right? We need 2 things from that. We need a big R and a little r. So the way I think about it is that big R is the farthest point from axis, and little r is the closest point from axis. Okay, where this is my axis of revolution. Small distance, big distance. Big R, little r. The process that we used in the previous example is exactly the same process we're going to use here. We're going to find the volume of that one washer, and then we're going to integrate all the washers using the formula we had from before. Okay, we good? Yes? Okay. So this is what it's going to look like. You get some funkier shapes here. They usually have holes punched through them in some way, shape, or form. That's like a dog cone. You know what I'm talking about? I don't have any dogs, but I know what they look like. Use them on my kids. Oh, what was that from? Oh, that's right. Yeah, the movie that killed me for the first half hour. Okay, another examples of what happens when you spin weird shapes. A lot of those areas that we did in the first section, when you start spinning them, are going to generate these weird looking things with holes punched through them because a lot of the areas didn't actually touch the axis of revolution. Okay, so let's look at that. I mean, we knew this already. This is just the calculus application of the volume of the disk. Big R squared minus little r squared dx. Don't forget the pi out in front. Now, common mistake. This is not the same thing as okay. You know that, right? Just say yes. Good. Okay. However you want to remember that, I don't care. But remember that it's the big cylinder minus the small cylinder. Get this out of your mind because we won't use that ever. Am I going too fast? We're good. Okay. Big radius and squared minus left. Yeah. Good. Another example. All right, let's just do one. Come on. Where are we going? Come on. Where? Got that. Where's my example? There it is. Sorry, I went right past it. Do you have the pictures?
No.
Oh, I should have had you draw pictures. Sorry, this is a common problem. It's commonly called a leaf problem or a cat's eye problem because it looks like a cat's eye, I guess. My rectangle is vertical, so I'll be working in terms of x. Is it perpendicular to the axis of revolution? Uh-huh. Is it touching the axis of revolution? Nope. So therefore, it's going to be a washer. Now, the graphic that I showed you does a nice job of showing you where capital R and lowercase r are. But, again, notice capital R is the farthest distance from the axis of revolution to a point on the rectangle. Little r is the closest point on the rectangle to the axis of revolution. And then those heights, again, remember, are not numerical. They are equational. Is that a word? I don't know. It is now. So I went a little click hungry on the last go around. Okay, outer radius, capital R, was in the picture. Inner radius, x squared. Notice that's also the same thing as top minus bottom, if you're feeling fancies in your panties. I like the outer radius and inner radius better, but if you want to use top minus bottom, you can. It'll show up again. And then we get that big, scary, long, well, that was not too scary, that's pretty manageable. And again, look where the squareds are. They're on the individual functions, not on the difference of the functions. Hopefully you picked up on this side note from the area, but we cannot get a negative volume. If you get a negative volume, you did something wrong. Most commonly, a negative volume comes about because you switch the location of these two. I would check that first if you get a negative answer. Instead of doing top minus bottom, you maybe did bottom minus top.
So we take a negative volume?
Should not, no. We'll see later. How are we doing? Good? Not so bad, yes? Okay, so let's ramp it up a little bit. Yeah, I just finished solving the problem. 3 pi over 10 if you're interested. Whether you F and int that or you do it by hand. That's one you should be able to do by hand. Easy peasy lemon squeeze. So now let's make things more interesting. What if you're not spinning around the x-axis or the y-axis, which we'll come back to in a little while? What if you're revolving something around the line, I don't know, y equals 2? By the way, y equals 2 horizontal or vertical? I'm sorry? Horizontal, correct. X equals is vertical, y equals is horizontal. Freshman cute. So we're still going to use top minus bottom. We're still going to use right minus left. But, okay, hold on. Let me back up. Let's go back to this problem. When I was looking for that big radius, if I look at this picture here, when I was looking for that big radius, I actually did top minus bottom. Okay, the top here is the square root of x minus the bottom, which is 0. But we're all smart enough to know I don't have to write the minus 0. When I'm looking for the little radius, I'm doing the top, which is the x squared term, minus the bottom, which is 0. Again, we don't need the minus 0. The only thing we're going to change in the next example is we're going to all of a sudden not be minusing 0. We're going to be minusing 3. second. You have, what did I give you for that? You have the picture and the equation? Okay, beautiful. All right, where's my region? Bounded by x squared plus 2. Okay, that's in red. The line 1/2 x plus 1 is the light blue. X equals 0 is the y-axis. And x equals 1 is the dark blue. So we're talking about this region here. And I already have my representative rectangle. What I didn't include, let me get a different color here. What color aren't I using? Orange. We're going to revolve it around that. It seems repetitive, but I'm going to go through it again since our first day doing this. Is my rectangle vertical or horizontal?
Vertical.
Vertical, therefore everything's in terms of x. That's easy. Is it perpendicular to the axis of revolution? Yes. Good. That wasn't meant to be a trick question. Is the representative rectangle touching the axis of revolution? No. So therefore, washer. Good. Okay. Now, I need to solve for a couple distances here. I need capital R, and I need little r. On your picture, please draw in where capital R is and where little r is before I show you. I'm assuming you can all find this, but just to make sure you're with me. Smell it. Does that smell weird? Smells like a rose, right? You don't like, you want to throw it out? Oh, okay. All of a sudden you're going to keep it. I see. You don't smell that? Go ahead. Okay, we good? Hopefully you have this as capital R and this as little r. We good? Okay. Okay, so let's start with capital R. Finding the length for capital R, we go back to the concept of top minus bottom. What's on top is the orange line, 3. What's on the bottom is the light blue line, which is 1/2 x plus 1. So capital R would be equal to 3 minus the quantity, 1/2 x plus 1. I'm going to stop there before, I'm going to stop there, comma. Do you understand that? Good? Any problems? Okay, good. Then, if that's the case, what's little r? Patrick, say it loud, say it proud.
3 minus x squared plus 2.
Beautiful. I think we've done the hard part. The rest is just calculation based. Okay, so the volume. By the way, remember when I said last chapter or last section that denoting it as an area or a volume is important? It becomes increasingly important now because we are finding a volume. Pi times the integral. Where are we taking rectangles from and to? Where's the first rectangle start? 0. And where's the last rectangle? Yes, 1. Thank you. Capital R, 3 minus the parentheses 1/2 x plus 1 squared minus 3 minus parentheses x squared plus 2 squared dx. Make your life easy. Simplify what's inside of that before you square it. That's actually 2 minus 1/2 x. Or 1 minus x squared in the second one. Questions? We're good? Let's suppose I took, instead of the line y equals 3, I moved it down to say y equals -1. It's the same idea, except we would be subtracting top minus bottom, so it would be the function minus -1. In my opinion, that's why the pictures can be very helpful, because you can see that top minus bottom. You can see that capital R and little r from the picture. Questions? We're good? Okay. We're going to stop there. Let's take a 3-minute break. Just because some of you look like your brain's going to melt. Okay.
Bolus is the bolus.
So the one thing we haven't looked at yet is every one of the examples I've given you, whether it was a disc or a washer, our rectangles have always been vertical, and everything you've been doing has been in terms of x. Those are, in my opinion, the easiest, because that's just how a lot of your brains work. But now what happens if it doesn't work as well in terms of a vertical rectangle? We saw some examples of this when we were doing the areas, and sometimes you're going to be forced to use a horizontal rectangle. It's fine, it's the exact same thing. So let's do this puppy. Find the volume of a solid created by revolving the area bounded by y equals x to the 5th, y equals 1, and y equals 32 around the y-axis. Different axis of revolution. Because our axis of revolution is vertical, our representative rectangle has to be horizontal. So now all of a sudden we're working in terms of y. Draw that picture first, shade your region, draw your representative rectangle, and then we'll get after it. How do you draw an x to the 5th? I don't know. Wie weiß es nicht? Sehr gut. Nicht sehr gut. Nein, keine Ahnung. I have no idea. What's a graph of x to the 4th look like? How about x to the 6th? X to the 8th? They all look like parabolas. X to the 5th looks like a cubic, just a little different. It climbs faster. If you're not sure, then get out your calculator and Desmos it.
My calculator today because This is the only class that I'm not like I did not want to think about it. There's so much
Stop, I'm emotionally fragile today.
All my other classes, alright, I can like take that again. Like, oh, I already know it.
So well, I feel like it's like a low standard to like get a 4 on this. Like you said, like to get a 5, you have to get over half. Just like half.
Yeah, but I'm barely getting like.
That's good.
I'm barely getting over half of them these quizzes.
I'm not like for one unit. Now you want us to do like every, all of the units at once. If I could only avoid this,
I gotta get a 4.
really for
Okay, let's do this. I don't have a picture, so I'll draw a picture. Okay. So,
Start talking.
most importantly, is my rectangle perpendicular to the axis of revolution? Yes, then I can proceed. Number 2, is my rectangle horizontal or vertical? Horizontal, which means, you already guessed, we're working in terms of y. If we're working in terms of y, the first thing I'm going to do is say that this is that. Which you all knew, right? Is my rectangle touching my axis of revolution? Yes. Therefore, I have a disk. What's the radius of the aforementioned disk? I'm actually going to keep it even, I'm going to make it more difficult than it should be. I'm going to do right minus left. Y to the 1/5 minus 0. Square that times pi times, be careful here, dy. The variable that you're working with and the differential have to match. Where am I taking rectangles from and to?
Why did you have -0?
I'll get there in a second. Where am I taking rectangles from and to, sir? One to 32. Did you say 32 or 36? You did say 32. Okay. Why did I add the -0 in there? Because I'm showing you what happens if it's not the x-axis. You're still going to do right minus left. So if I move that axis of revolution over 1, things change. Okay. And based on what Danny said, of course, we're not going to do that because we're all pretty bright. Y to the what? 2/5. Just want to make sure. And I'm going to assume that you can find that definite integral. Whether you FN int it or you grind it out by hand, that's not a difficult antiderivative to take. The number's a little nasty though. What's, just for giggles, what's 32 to the 2/5 without using your calculator? 4. Why?
Because 32 to the 1/5 is 2, squared is 4.
It is. Good. You didn't take 32 squared and then take the 5th root of it? No, you're very smart. Good job. Okay. Now, how do we change this? Well, we could move that figure off the axis of revolution or change the axis of revolution. For instance, I could say instead of spinning it around the x-axis, let's spin it around the line x equals -1. Now all of a sudden it becomes a washer. We have to worry about a capital R. We have to worry about a little r. We have to worry about right minus left. So these problems can ramp up very quickly. Take your time, draw a good picture. It doesn't have to be accurate, but it's got to be a sketch that you can work with. Draw your representative rectangles and ask yourself a series of questions. The goal, obviously, is to get to this. Solving that definite integral is a key element, but it's not the deal breaker in my opinion. My focus and your focus on these problems should be getting it set up. Does that mean you can FN into every homework problem? No, you should probably practice some definite integrals, especially where they involve taking the square of a binomial. Those practices are good for you, but for the most part, it's the setup that's more important. Questions so far? We're good? Okay. Oh, yeah. So, just a quick summary, what we talked about already. You know that already. whether it's horizontal or vertical, whether if it's touching, then we have the disk method. And then what about something like this? Okay. The rules from area still apply. So notice in this problem, I'm working with horizontal rectangles, so everything's in terms of y. But when I get to this point at 1, the left-hand side of that rectangle changes. Anytime the right or the left-hand side changes, we need a separate integral. However, I would not do a separate integral because what shape is that when you spin it? Okay, so notice the three-dimensional figure. I've got this cylinder with a little cup thing carved out of it. From this point downward, what shape is that? It's a cylinder. So I wouldn't do calculus to find the volume of that bottom part. I would just calculate the volume of a cylinder. If you want to do calculus, it's okay. You'll get the same answer. Okay, and then the top is similar to what we did already. And again, your capital R here would be the right, which is 1, minus the left, which is 0. And then little r would be the function minus 0. Very good.
Are we only doing it with respect to y because that's what it tells us?
Yes. You could also do this one with respect to x, right?
Yeah.
Well, the reason you're doing it with respect to y is because you're revolving around the y-axis. Yeah. This is what makes the difference. Because again, remember our rectangle has to be perpendicular to the axis of revolution. Otherwise, we can't solve it. Yeah, it would be nice and easy if it was x-axis, because then we just, and we're done. A little uglier. Okay. I don't care. Blah, 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 blah. Not exciting. More work in that. Oh, look at that. It's fun. Okay. Okay. Oh, I went too quick. Everett is convinced that none of you will get this joke. Washer and that's a floppy disk. Do you know who that is? Yeah, it's Method Man. No? Maybe you're shaking your head. Huge fan?
I mean,
You know the name.
I know who Method Man is, yeah.
Right. You especially like his second album, right?
I like, he was in that movie, Keanu. I don't know if you ever saw that.
No.
Well, that's where I know him from.
There's a
It's
movie called Keanu.
It's a Key and Peele movie.
Wait, I think I have seen
Yeah,
that.
yeah.
It's kind of like a parody of John Wick or something?
Yeah.
Okay.
Watch.
What's that?
You might have to watch.
We might have to. Yeah. We'll have plenty of time after the AP test.
No.
But of all the things we could do after the AP test, I don't know if Keanu is the right way to go.